Okay, so second section we're going to look at this week is on what we call rational zeros and synthetic division. So it's kind of two parts, but they're definitely connected. In the book, okay, when you see synthetic division, they call it Horner's algorithm, probably named after the person that did something to invent it or discover it. So keep that in mind when you read the directions. All right, so when we graph a function, like the one that we just had on the screen here, functions can have rational and they can have irrational zeros. What that means is they can cross the x-axis at spots that are rational and spots that are irrational. Okay, so if you remember what that means, rational means it's a number that you can write as a fraction. Like 0.5 you can write as a half. 0.75, 3/4. Okay, numbers that you can write as fractions are rational. Numbers that you can't write as fractions are irrational. Okay? Like the square root of 2. 2 square root. No matter how hard you try, you will never be able to find a fraction that represents the square root of 2. I mean, I can prove to you it's impossible. You can't do it. So those are numbers you can't write as fractions. What I'm going to do is show you a theorem that gives you a way to find the roots that are fractions. The ones that aren't fractions, that's a little harder. Okay? But I can at least show you relatively easily how to find the ones that are fractions as long as your problem meets certain conditions. Okay? This doesn't work all the time, but if I give you a problem and I say use the rational root theorem, I'm going to give you a problem that it would work on. I'm not going to give you one that it doesn't. So, first of all, we have to start off with a polynomial. When I give you guys an actual problem, it might be something like that. 10x to the 5th minus 3x squared plus x minus 6. For now, I'm just going to represent something like that generically. So you'll have some type of polynomial. Usually it's written with the highest exponent first, and then the exponents go down each time till you finally end with a constant. The last number doesn't even have a letter, like minus 6. Okay. So we've got a polynomial. First of all, to use this theorem in your polynomial, all the coefficients have to be rational. What are the coefficients? Those are the numbers in front of the letter. All of them, however many there are. They all have to be numbers that can be written as fractions. Okay. A number like that is fine. It can be written as a fraction if you put it over 1. Okay. So an example of something that's good that would work, that one's good. 10, negative 3, 1, negative 6. All of those numbers I just said can be written as fractions. 2, negative 5, 1, 3. All of those numbers are fractions, so that's good. Okay, no problem there. If I did something like this, now we can't use the theorem. Because now you've got a number in front of x that's a square root. And it's not a nice square root. Like if it was square root of 9, that would be okay. But square root of 10, it's a number that you can't write as a fraction. So if you had a square root in front of the x, you can't do it. Unless it's square root of 4, square root of 9, square root of 16.
The square root of a square.
Yeah, the square root of a perfect square. Yeah, but they wouldn't do that. So all the numbers in front have to be numbers you can write as fractions. And the key is that the first number and the last number can't be 0. This doesn't work if the first number and the last number were 0. So if I go back to the problem we're going to do and I get rid of this, can't use the rational root theorem on it anymore. It doesn't work. Because you don't have a number at the end. It's like plus 0 right now. So the first number and the last number can't equal 0. All right. So if you draw that, Okay, and it's going to cross the x-axis somewhere that's a fraction. Okay, we could write it like this. We could write the answer as a fraction. Okay, assuming that it crosses somewhere that is a fraction. We could write it as p over q. The only thing we have to figure out is how do you get p and how do you get q? How do you get those two numbers? Well, the two numbers come from up above. In fact, they only depend on this one and this one. So when we go through and do the next problem, the only numbers that are important here for the rational root theorem are 10 and negative 6. Those are the only two numbers you need to use. So p has to be a factor of the constant. The constant is the one at the end. It's the one without any letters. So if you can find a rational root or a rational zero for your polynomial, the numerator has to be a factor of the constant. And the denominator is a factor of the number in front. Okay, remember, factors are things that divide into without remainder. So, like factors of 20. 1, 2, 4, 5, 10, 20. Those are your factors of 20. Okay, so the numerator is a factor of the constant. The denominator is a factor of the leading coefficient. Now, what we're going to be doing is generating a list. Sometimes the list gets kind of big. You can have 10, 20, you can have a lot of different answers in it. Not every single number that we make in this list is a root. Okay? I want you to think of this theorem as generating a list of possibilities. That's all that it does. It gives you a list of options. You still have to go through and look at that list of options and narrow them down. How do you do that? That's where the graphing calculator comes in. All right, so again, now that you guys get calculators, that's how we're going to take our list of possibilities and we're going to cross out ones that don't make sense using the calculator. Okay. So, example 1, I'm just going to change the wording a little bit. List all possible rational roots or rational zeros. In other words, make me a list of all the places that this graph could cross the x-axis. Okay. All right, so first thing we want to do is just figure out what are our options for p and q. P is a factor of the constant. Isabel, what's the constant here? -6 or +6. Those two numbers have the same factors. Can someone tell me all the numbers that divide into 6? Yeah?
1, 6, and 3, 2.
So 1, 2, 3, 6. That's half of them. There's 4 more. Yeah?
-1, -2, -3, -6.
So positive or negative, 1, 2, 3, 6. So there's 8 numbers that divide into our constant. Q is a factor of the leading coefficient, so 10. What are all the numbers that divide into 10? Those are my factors.
1 and 10, 2 and 5, positive and negative.
Yep. So positive or negative, 1, 2, 5, 10. I just put them in numerical order, but that's not critical. Now, if there's a rational root, it's of the form p over q. So now you have to write all the different p over q's you could have. Every different p divided by every different q, which seems like it could be kind of hard, but as long as you do it systematically, it's not bad. So we'll start with the first one. Let's let p be plus or minus 1, and we're going to put it over every different q. So we have plus or minus 1 over 1, plus or minus 1 over 2, plus or minus 1 over 5, and plus or minus 1 over 10. Those are all the different possibilities you could have with a 1 for p. Now we're going to do all the possibilities you could have with a 2 for p. So we'll do 2. And we might get some repeats. Okay, we will get some repeats. So what would be the first one starting with 2 for p? It would be plus or minus 2 over 1. So plus or minus 2 over 1. What would the next one be? Yeah, it would be plus or minus 2 over plus or minus 2. We already have that one. That's 1. So we don't need to do 2 over 2. How about plus or minus 2 over 5? Do we have that one? No. And how about plus or minus 2 over 10? Do we have that one? We already have plus or minus 2 over 10. That's 1/5. So we don't have to write that one. Okay, so this is what usually happens. You get some repeats. Let's do 3. Plus or minus 3 over 1. Do we have that one? No. Plus or minus 3 over 2? No. Plus or minus 3 over 5? No. How about plus or minus 3 over 10? No, we don't have that one. So we didn't have any of those. And then the last one, now we do it with 6. Plus or minus 6 over 1. We don't have that one. How about plus or minus 6 over 2? Yeah. That's 3. We already have that. Plus or minus 6 over 5? No. And how about plus or minus 6 over 10? Yeah, we have 6 over 10, that's 3 over 5. So there's our list. And that's the answer. List all possible rational zeros. There they are. So if this graph crosses the x-axis, at a number you can write as a fraction, it has to be in this list. Okay? I'm not saying it crosses at every one of these spots. I'm just saying this is a list of options. In the next problem, we're going to narrow down this and kind of limit our possibilities. But any questions on just generating a list of possibilities? This is a bigger one, probably the biggest one we do today because we've got 4, 6, 10, 12, double it for negative, so there's 24 different places it could cross at a rational number. Okay, now, using that list, we're going to answer this question. We're going to show that that graph, which is the same one we just did, crosses the x-axis in one spot, so there's one root, and that it's irrational. We're going to show that the one place it crosses the x-axis is a number you cannot write as a fraction. So we're going to use a graphing calculator to help us out. So we've got 10 x to the 5th minus 3 x squared plus x minus 6. So what I'm going to do, okay, so there's our graph. Let me just make sure I typed everything in right. I think I did. 10x to the 5th minus 3x squared plus x. Yep, that's good. So let's keep this here. And let's get our list of roots. And let's look at the graph. Okay. It's a little small, but where does it look like that graph crosses the x-axis? Well, that's the y-axis, up and down. So x-axis. Looks like it's near 1. So does it look like it's near plus or minus a half? No. Doesn't look like it's near that. Does it look like it's near plus or minus a fifth? No. Plus or minus 1/5, that's 0.2. Doesn't look like it's close to that one. Plus or minus 1/10? No. Does it look like it's near +2 or -2? No. So a lot of these options we created, they don't even look reasonable. 2/5, that's 0.4. No, it's not near plus or minus 0.4. It's nowhere near plus or minus 3. 3/2, that's 1.5. Does it look like it's near 1.5? Negative 1.5? No. 3/5, that's 0.6. 3/10, that's 0.3. Plus or minus 6, it's not even close to those. Now 6/5. 6/5, that's 1.2. I mean, maybe when we zoom in more, I mean, maybe you could argue it could be close to 1.2. I don't think the negative 1.2 is even close. So out of that list, the only one that looks even close was +1 and +6/5. So if this were a question on the test and I said, using your calculator, eliminate the ones that don't make sense, you would do what we just did, and I say list the ones that still work, or list the ones that seem reasonable, I would say 6/5 and +1. Now let's check it. Let's go second, calc, 0. Pick a point left, pick a point to the right, and do your guess. And the answer is 0.9505. Why does 0.9505 have to be irrational?
Because it's none of the possible ones that we had.
Yeah. It's none of the possible ones that are rational. If it's rational, it's got to be one of those numbers. And we narrowed it down to this one and +1. Well, it's not 6/5, that's 1.2. It's not +1. It's something else that's not in the list. So if it's not in the list of rational, the only other option, it's irrational. Right? So that's what I'll write down. So since the root is approximately 0.9505, and this number is not in our list of possible rational roots. It's not in the list of rational roots. It must be irrational. It must be irrational. I don't know if you can shorten that up at all, but that's basically the explanation. So the root is approximately 0.9505. It's not in the list of rationals. It must be irrational. How could you get 0.9505 by hand? That would be another question. That's a little tough. Probably couldn't do this kind of problem by hand at this point. Okay. So we will do some network. Okay, this one, obviously, we didn't get any numbers in this list, so all of these possibilities, none of them actually work. So we'll do something that do in a little bit. Okay, so that's the idea of the rational root theorem. Any questions on that? Okay, once we learn synthetic division, I'm going to tie this in with that, and we'll do another one of these kind of problems, but it's going to be a much shorter list. Much, much shorter. That's the biggest one we do today. All right. Does everyone have that wants to copy it? Okay. So we learned long division yesterday. Long division is good because it always works. Well, if you want to divide by something that's simple, and by simple, I mean it has to look like what's in that box. It has to be x minus a number. If you're dividing by something simple, there's a shortcut. It's called synthetic division. Now, could you use synthetic division in cases where it doesn't exactly look like that? Yes. I'm not really getting into how to do that. I'm only showing you how to use synthetic division in the simplest case. X minus a number. All right, so what I'll do is I'm going to show you the steps for synthetic division, and we'll kind of do a problem at the same time. There's 4 steps. Probably fit them on 4 lines. And then leave yourself room below that to do an example. All right, so in example 3, we're going to use synthetic division to show that this number is a 0. But I'm not going to show that directly. I'm going to show something that means the same thing as that. Okay? If we look at what we did yesterday, showing that a number is a 0 is the same as showing the number is a root. It's also the same as this, showing that x minus the number is a factor. That's what I'm going to show. Instead of showing, let me go back here. Instead of showing 3/2 is a 0, I'm going to show something equivalent. X minus 3/2 is a factor. So if I can show x minus 3/2 is a factor, then that answers the original question, that it's also a 0. Now, when something's a factor and you divide it, what's your remainder? 0. That's the whole goal. I'm going to divide something into something and hope for a remainder of 0, which means what I divided by is a factor, which means that number is a 0. Okay, that's what I'm going to try to do. Okay. Any questions on that idea? We're going to show something is a factor, which is going to prove that the number is a 0. The quick way to show that it's a factor is use synthetic division to divide it. So let's look at synthetic division. So we start by writing down C. Just to be super clear, C is the number after the minus sign. You ignore the minus sign. Okay? So let me write down what we're doing. We're doing this. That's the problem I'm about to do. I'm going to show that when I divide by the factor x minus 3/2, x minus 3/2, I get a remainder of 0. So you start by taking the root, which is the number after the minus sign, putting it on the outside of a bracket. And now these dashes are all the coefficients that you have to fill in. Okay? You're not going to write any letters in the whole thing. If you're missing a power, you fill in a 0. So the highest power is cubed. I have a 2. Squared minus 5 to the first power. That's just a 1 in front of the x. And then I finish off with my constant. Okay. Any questions on setting that up?
I don't know what just happened.
Can someone explain how I got those 4 numbers? Yeah.
The coefficients on the top, like 2x, 5x, x3.
Yeah. They're all my coefficients of the numbers that I just circled. 2, -5, 1, and 3. Okay. Any questions on where the 2, the -5, the 1, or the 3 came from now? And then the number on the outside of that bracket, the C. C is the number after the minus sign, which in our case is going to be 3/2. Any other questions on just setting that up? Okay, so the next step is to bring down the first coefficient. So we're going to bring down the 2. I would do it like this. Put a line, bring down the 2. All right, so you get your first coefficient. Now, we're going to multiply the number that's on the outside, 3/2, times the number we just brought down, and we're going to put the answer right there. So multiply the divisor, that's the thing on the outside, by the first coefficient, that's the thing I just brought down, and write the answer, write the result, below the second coefficient, where I put the question mark. So I'm not going to put a question mark. So let's multiply them first. What's 3/2 times 2? Yeah, 3. 3 halves times 2 is 3. Put the answer right there. Any question on how we got 3? Think of 3 halves as 1.5. It's 1.5 doubled. It's 3. Now, this is the part that's a little different from what you do in regular long division. In long division, you subtract your columns. Add. So take the two numbers that are in the column, -5 and 3, and add them up. So -5 plus 3 gives me -2. Any question on how I got the -2? And now we keep repeating that process till we're done. You know you're done when you finally get the number that goes right there. So we got to keep going till we fill all this in. So repeat until you're done. I'm not going to show you yet what the last row means. Okay? I'm going to see if you can guess by what the answer we're going to get. I think you'll know what it means. All right. Now we do it again. What's 3 halves times -2? -3. 1 plus -3. Add those up. What do we get? -2. So, really, we're going to do the exact same thing again. 3 halves times -2. -3. And now add that column. 0. What do you think the 0 is?
Remainder.
That's the remainder. Yep. So that's the remainder, which is perfect because they said to show that, well, I showed that x minus 3 halves is a factor. How did I do it? I showed that it went into it without a remainder. So if x minus 3 halves is a factor, that means what I had for C, 3 halves, is a 0. So I showed what they wanted to show. Now, there's other stuff there too. That 2, the -2, -2, that's my quotient. So this part is your quotient. This part is your remainder. So if you're like, well, how is that your quotient? The -2 is a constant. The other -2 is my linear term. The 2 is my squared term. 2x squared minus 2 with an x, and then a -2. So these 3 numbers came from those 3 spots. Okay, that's my quotient, and my remainder is 0. So now, the directions say, well, to factor. Well, I already know one of my factors. I proved x minus 3 halves is a factor. So if I wanted to factor, just write down the original problem. It's 2x cubed minus 5x squared plus 1 plus 3. If you wanted to factor this is a little harder than factoring normal, like quadratics.
No, it should be plus 1x.
Was the original problem?
Yeah, you can
2x cubed minus 5x squared plus x plus 3.
Plus 1 plus 3.
Yeah, thank you. That's important. So if we wanted to factor that, we already know x minus 3 halves is a factor. That's one of them. And now think back to what we did yesterday. If I wanted you to factor the number 12, just like what we're doing here, and I tell you one of the factors is 3, how do you get the other one? You divide. We already did divide. We know if we divide this by that, you get the other factor. Well, if you divide this by that, you get the other factor. What's the other factor? It's sitting right there. That's the answer when you divide. 2x squared minus 2x minus 2. That is how you would factor it. So we just have to get one thing that we know is a factor, and then the quotient when you divide, that's the other factor. The only thing that was a little different in this problem is they gave you 3 halves. They gave you a rational root to try. Eventually, you're going to have to figure out the rational root to try. How do you do that? That's what we did in the first problem. You make a list, and then you check on the calculator which ones work. All right. So between the first problem and now this problem, we just have to put the two together and kind of do a whole problem. This is the long part, the synthetic division, but I think it's still shorter than what we did yesterday. And it doesn't take up as much space. So once you put it on your paper, you don't need to like keep going down into the right. It's kind of how long division ends up. It all fits in this space right here. All right, so let's use just a basic one. Use synthetic division, and I just want to know the quotient and remainder when I divide this. Now, what I divide by, it's supposed to look like what? X something and then a number. If you want to use synthetic division, it has to look like what? Give you a hint, it's not like that. That's not what we did on the last one. It's supposed to be x minus a number. It has to be x minus a number. Well, this is close enough that you should be able to think of it as x minus a number. It's not like it's x squared or something. That now you can't do anything. You've got to go back to long division. But how can you think of this as x minus a number?
X minus a negative.
Think of it as x minus a negative, right? So we're dividing by x minus. Here's the number. So you always take the number that's after the minus sign. And that's what goes on the outside of the bracket. So in the last problem, the number after the minus sign was a 3 halves. In this problem, it's a -3. Okay. Can anyone tell me my coefficients that I would put next to that? You got to be careful. Yep. Okay.
3, 7, 1.
Okay. I'll put that there for now.
-11.
And -11. We forgot one thing. Why did I leave a gap? Kind of left like what looks like a gap there. Yeah.
It should be 0.
Yeah.
Squared.
So everything there was good. The only thing we got to remember is to put in a 0 for the x squared. Okay. And now we don't have any fractions here, so the arithmetic this time should be really fast. Bring down the 3. What's -3 times 3?
-9.
-9 plus 7?
-2.
-2. -3 times -2?
6.
6 plus 0?
6.
6. -3 times 6?
-18.
-18. Plus 1 is -17. This will be the biggest calculation we have. -3 times -17. -3 times -17, 51, and then 51 minus 11, 40. So, what does that mean about x plus 3? It's not a factor, which means -3 is not a root. Okay. So if you were trying to factor this problem, x plus 3 is not the way to do it. So you got a remainder of 40. And a quotient of 3x cubed minus 2x squared plus 6x minus 17. That's your quotient. So I guess I should probably write it out. So quotient, 3x cubed, and remainder, 40. So much faster than long division, takes up much less space. But you can only use it if it's x minus a number. All right. Let's show that 3 is not a 0. I'm going to go back to that chart that we had yesterday for a second. I'm not going to directly show that. Instead of showing now I'm going to bring up the chart. Instead of showing 3 is not a 0, I'm going to show that x minus 3 is not a factor. Now, to show something is not a factor, divide it. And if it's not a factor, you're going to hope that you get a remainder that's not what?
0.
Not 0. So that's what we're going to do. So put 3, fill in your coefficients, 2, 5, -2, -3. Make sure we didn't miss any. I think we're good. And now do it out. Bring down the 2. 3 times 2 is 6. 5 plus 6 is 11. 3 times 11 is 33. Plus -2 is 31. This doesn't look like we're going to get a remainder of 0 anytime soon. 31 times 3 is 93. Plus -3, that's a remainder of 90. So we just showed that x minus 3 is not a factor, which means 3 is not a root. Okay, any question on that one? It's kind of another practice with synthetic division. All right, so now we'll kind of put synthetic division and the rational root theorem together. So if you get a problem and it asks you to find all rational zeros, these are kind of the steps you want to go through. The first thing is start with the rational root theorem. Make a list of possible options. The second thing is to use the graphing calculator. Use the graphing calculator to cross out the ones that don't make sense. And then the third thing is once you find one that does make sense, that does work, use synthetic division, divide through by it, and then you're good. Because once I can turn this cubic into a quadratic, then I can solve it. I have a quadratic formula. So I'm just going to go back for 1 second just to show you. We already did a cubic earlier. Look what happens when we started with a 4th degree problem. Look at your quotient, 3rd degree. Every time you divide through synthetically, you take the highest exponent and bring it down 1. So if I'm starting with a problem that has an exponent of 3, and I divide synthetically 1 time, it's going to come down 1. It's going to come down to a 2. And once I get it to a 2, then I can use quadratic formula. So that's the goal. Get it from a 3 down to a 2 through those steps. Okay, so let's start with P and Q. Okay, P are the factors of my constant. My constant here is -2. What are the numbers that divide into -2? Yep, plus or minus 1, plus or minus 2. That's it. So I told you the first one we did would be the biggest one. This one's much smaller. Now there's no number there, but we can put a 1 in front. What are the factors of Q, which is the number 1? Just plus or minus 1. So when we write out all the different options, there's not that many. Plus or minus 1 over 1. Plus or minus 2 over 1. That's it. So if this is going to have a rational root, it's going to cross the axis in one of these 4 spots. Plus 1 minus 1, plus 2 minus 2. Now I'm going to use the graphing calculator to figure out if it is one of those 4. Alright, so we've got x cubed minus 3x minus 2. And it might even be a couple of these. We'll see. It looks like it could be -1, and it looks like it's positive 2. Now, this is something special. The fact that the graph comes up and it actually is touching the axis and bouncing away from it, that means something. I'll tell you later what that means. Okay. But it is coming up, it's touching the axis and bouncing away from it. And then it's crossing again. So I would say -1 looks reasonable, positive 2. Nothing else. So what I'm going to do is I'm going to check one of them on here. I'm going to go to my table. I'm going to type in positive 2, and I'm going to hope that the y value is 0. If it is, I just found a root. Yep, 2 is a root. So what I'm going to do now is divide by 2 synthetically. So I'm going to make a list of my roots. 2. And now we're going to use synthetic division, and we're going to divide this by the factor x minus 2. I already know it's a root, so my remainder is going to come out to 0. But what I'm interested in is the quotient. I want to know the quotient when I divide. So let's do 2, and then 1, 0, negative 3, negative 2. All right. 2 times 1 gives me 2, and then 0 plus 2, 2. 2 times 2 is 4 plus negative 3, 1, and then 2 times 1, 2, and negative 2 plus 2 is 0. We already knew that would happen. So now, if I was trying to factor this, I know that x minus 2 is a factor, and my other factor is right there. X squared plus 2x plus 1. That's the other factor. Now focus on that. Find the roots of that problem. Well, sometimes you have to use quadratic formula, but that factors nicely. Anyone see how I would factor x squared plus 2x plus 1? It's going to factor into two things that are the same. Yep.
I'm not sure if it's right, but it's just x plus 1, x minus 1. Or, oh no, it's x plus 1 and x plus 1.
Yep, it's x plus 1, x plus 1. So we know if we plug in 2, we get a root. What would I have to plug in here to get a root? And what about here? It's a repeated root. So there are 3 answers, but negative 1 is repeated. It's called a double root. And the way you can tell if you have a double root is when you look at a graph. If the graph comes up, it touches the axis and bounces away from it without crossing. That usually means you have a double root. So I already knew just by looking at the graph, we were going to get a double root. Okay? So that's the process. Use the rational root theorem, synthetic division, and then solve the last part. I can't tell you how to always solve it. It might not have been factorable all the time. You might have to use quadratic formula sometimes. Questions on that one? All right. That's kind of the same. That's kind of the same. We'll just do one of them. It's up to you. Want to do 7 or 8? Eight? Okay, so 8 is asking you to find all the roots, whether they are rational or irrational. So that means if you need to use the quadratic formula, do it. 7 is kind of like the last ones. Just find the ones that are rational, only the ones that come out nice. If they're going to come out nice, you're going to be able to factor it. If you can't factor it, that's when quadratic formula comes in. Okay. So, start with P and Q. What are the factors of P in this case? Plus or minus 1, plus or minus 2. What are the factors of Q?
Plus minus 1, plus minus 3.
Yep. So not a ton of variety, but a little bit. We could have 1 over 1. We could have 1 over 3. We could have 2 over 1 or 2 over 3. So if it's going to cross the x-axis at a nice number, it's going to be one of those 8. How do we narrow the list down? What do I do next? Graphing. All right, so graphing. So we've got 3x cubed minus 8 8x, there we go, squared, plus x plus 2. So we're looking between positive 2 and negative 2. All of these numbers are between positive and negative 2. Which ones look reasonable?
Negative 1 over 3.
I would say negative 1 over 3, probably not the positive. So it could be negative 1 over 3. What else?
Positive 2 over 3.
Yeah, I'd say positive 2 over 3, probably not the negative though. Plus 2? No. Minus 2? No. Plus 1? Not really. Minus 1? No. So hopefully negative 1/3 or positive 2/3 works. Let's check negative 1/3. Negative 1/3. No. Negative 1/3 is close, but it's not 0. So even though it looked reasonable, and I thought it looked reasonable, it's not. Let's check 2/3. 2/3? Yep. 2/3 is a root. So if we're making our list, 2/3, and it's said to classify as rational or irrational, that's rational. Okay, and now let's get the other one. What am I going to do next with the 2/3? Yep. We already know what the remainder is going to be. We don't care about the remainder. It's going to be 0. I need the quotient to get the other two roots. So we've got, I lost the original one. So 3, negative 8, 1, 2. 3, negative 8, 1, 2. Bring down my 3. What's 2/3 times 3? 2. And then negative 8 plus 2? Negative 6. Now this part you can do with a calculator or just think in your head. What's 2 times negative 6? Negative 12 divided by 3. Negative 4. Okay, so you can do it in your head like that. 1 plus negative 4 is negative 3. What's 2/3 times negative 3? Negative 2. Remainder 0. I already knew that. That's what I'm interested in. 3x squared minus 6x minus 3. Now I don't have to, but I could divide everything by what to make everything smaller? 3. You don't want to? Don't. But I think you should. Yeah. Now, two numbers that multiply to give me negative 1 and add to give me negative 2, not going to happen. You can't factor that. So what does that mean I have to do with it? Got to do the quadratic formula. A is 1, B is negative 2, C is negative 1. Since I can't factor it, I already know the other two answers are going to be irrational. Which means they're going to have square roots in them. Okay? Let's go through and see what they are. So negative b plus or minus, what comes next?
Square root of b squared.
B squared, yep.
Minus 4ac.
4ac, okay.
All over 2a.
All over 2a. So just simplify that and that's your answer. 2. We have minus a minus. What happens there?
Positive.
That's going to turn into a positive. 4 times 1 is 4. 4 plus 4 is 8. And now, how does the square root of 8 reduce?
Like,
Get the 2 square roots.
yeah.
2 square roots of
2.
2. Right? The square root of 8 is the square root of 4 times the square root of 2, which is 2 square roots of 2. And now that you did that, what do you have in common everywhere? Not under the root.
2.
A 2. You can't touch what's under the root. But you can do it 1, 1, 1. In fact, if you want to reduce in the quadratic formula, it has to do all 3 spots. So 1 plus or minus the square root of 2. Those are my other answers. Without finding the rational root of 2/3 first, we could have never done this. If you can't get a rational root, you can't do synthetic division, you're stuck. So I'll always give you one that has a root that works. Okay, any questions on that one? So that's synthetic division and rational root theorem. Okay, so the homework, tonight there's no range of problems, it's just individual ones. So 1, 2, 5, 6, 9, 10, 13, 14, 17, 18, 27. Also, don't forget, tomorrow we have the pictures. They're doing pictures at 11:25. So we'll stop for that. You don't have to order them, but I guess we just have to go down and do them. So we'll do that, and then we'll come back up and finish after that.